Okay, then so we start today's lecture. So basically, we started studying signal space. The reason being that for the description of digital modulation schemes, which will be done towards maybe 3-4 lectures ahead, we will be doing all those digital modulation schemes, which you already know from the course on Introduction to Communication Systems, that is QPSK, QAM, UPSK. For the efficient representation, we require some concepts of signal space. Okay, since you have already undergone a course on groups and linear algebra, or linear algebra you have studied elsewhere, you are familiar with the concept of vector space, basis functions, and all these things. Hence, we would be only defining, or we would be only saying things about what we need. Okay, so we need continuous functions of time, and that too in a domain, fixed domain, 0 to t. So we would be saying things pertaining to that only, assuming that you have some background on vector spaces, basis functions, and how to obtain the coefficients for the basis functions to generate a signal which lies in the space. Okay, so assuming this, we will be spending 1 or at most 2 lectures on it, and then we would start dealing with random processes. Okay, and then finally the modulation schemes, the detector design, because then we have built sufficient base for our study. Okay, so we were doing signal space. So in this, you are saying that let us say there is an ST, that is a continuous function of time, and it's a signal which is a full duration. Full duration means that it lies from 0 to t, or you can say that 0 to t is only is a point of interest of ours. Okay, 0 to t. Now, why this t, or why this finite time constant? Because generally this t will correspond to the symbol interval or the bit interval. So in a bit interval, we are studying the function s of t. Now, saying it's a real valued energy signal means its energy is finite. We want to consider those signals only, and there are several reasons for saying that we should only study finite energy signals for real implementation. We are not going into that, but you may correlate it with your signals and systems, or you may look out for it elsewhere, that why only energy signals are mostly studied. Okay. Basically, they lead to you can say a good analysis of themselves. But this property, that this square integration is finite, helps you derive several properties. Okay? And such signals obviously would be easy to generate as well, most probably. Okay? So I wrote it down that this is for the real, because we have written real value, but if at all this complex value, then you have to take the absolute value and square. Okay? That is the way to obtain the energy. Then why? So we now in the signal space, we would be dealing with the geometric representation of signals. It means, let us say we want an analogy between signals and geometry. Okay, if at all in geometry we have the concept of vectors, can we associate vectors to signals as well? That is our purpose. Okay. So the purpose and the motivation is that s of t in t belonging to 0 to t has infinite values. If I can associate a finite length thing to it, the study becomes easier. That is quite obvious. And secondly, for the purpose of generation, and for the purpose of usage as well, that if at all I can write st as sum of some standard functions. Let us say if I can write st as sum of 5 functions, then I only need to store in a lookup table those 5 functions and the coefficients for st, and I can generate st. Okay, and that it makes st a universal sort of a function, because it can be generated by any node if at all those 5 functions are available with it. Okay, so then we said that let us say we have set of m energy signals, and as linear combinations of n orthonormal basis functions. Now this orthonormal term simply means that all these n functions are orthogonal to each other. Secondly, each one of them has a unit norm, or their energy is, you can say, unity. They have been normalized. That's why this normal words come. Normal means that now by efficient normalization, their energy becomes unity. So it becomes orthonormal basis functions. Okay. So this is what we were doing, that n is less than equal to m. So we want SIT to be written as sum of these n basis functions which are orthonormal. The coefficient is Sij. The time domain is 0 to t. That is our you can say domain of interest or domain of study. And you have how many signals to represent? M signals. And definitely m will be greater than equal to n. That should be, because we must be able to generate a larger class of signals with the help of these capital N functions. Okay. Up in terms of vector space, this set of basis functions should generate all the elements of the vector space. Hence, this basis set should be complete. It must generate all the elements. Okay. So we have picked up some terminology from the study of vector spaces. And the way to obtain these Sij is to basically solve this integral. This integral is nothing but the projection of Sit onto phi jt. Okay, now this projection term again comes from the study of vector spaces. I will also spend some time on it once I move ahead with today's lecture. Okay. So this is what we did in the last class, in the last lecture. So we wrote that phi jt's are orthonormal. That is integral 0 to t phi it phi gt dt 0 delta ij. Now remember one thing, that this definition of this projection or this inner product assumes that both the signals are real. If at all they are not real, then you have to take a complex conjugate here. Sit into phi j star t. Similarly, phi it into phi j star t. So remember that. So this is all for the real case. So let us move ahead with today's lecture. So continuing from lecture 16, I am writing that each basis function is normalized to have unit energy. That is, we know that it is non-normal, they must have unit energy. And basis functions, but I am just writing what we have just written mathematically in the last, towards the end of lecture 16. So basis functions phi it, phi 1t, phi 2t, and phi nt are orthogonal with respect to each other. Over the interval 0 to 0. Okay, this is, I think, we have written whatever we have specified here mathematically or analytically. So that is what we have said, that the energy, first of all, they are, you can say, orthogonal, because if I is not equal to j, it is 0, and if I is equal to j, this gives you the energy of phi I square, phi it, that is integral 0 to t phi I square t. This is 1. So it means both the conditions are specified by this single equation, and we have just noted it down. Okay. Now let us see what is this set. So set of coefficients. Sij, where j is equal to 1 to n, may be viewed as an n-dimensional vector denoted as suppose we denote this. Okay, now it becomes a vector. This is an n-dimensional vector. The elements being Sij, j line from 1 to 2. Okay. Now remember that this now has a one-to-one correspondence. Okay, one-to-one relationship with the transmitted signal Sit. Now this is some sort of a larger statement, I would say, which I am restricted to not prove basically. Basically, इसका एक proof होना चाहिए. What does it mean is that it is saying that through this equation, Sit is equal to summation j is equal to 1 to n Sij phi j t. We have a one-to-one relationship. It means if given Sij, I can uniquely find Sit, and given Sit, I can uniquely find Si vector. It means all the Sij's. Now this means that this has to be a unique thing. So we are not proving it, we are assuming that this will happen, although it will have a definite proof. Very easy proof is there. But whatever we need in this course, we don't need to prove this. We only need to know that if given Sij, I can generate Sit uniquely. Given Sit, I can find Sij, all Sijs, j line from 1 to n. Okay. So this is pretty much what the statement says. And as digital communication engineers, no need to go into the proof of this right now. But I know it must have been done in some other course. And as usual, what I say that if at all there is an interested reader, you are most welcome to go towards the textbooks of linear algebra and see the proof. And maybe you can prove it yourself as well. I feel that it's easy. So what does this leads to? So let us see this relationship through this figure. So we have this towards the left, you have a synthesizer, and towards the right, you have an analyzer. Okay, this is called as synthesizer. Now, as the words say, synthesize means that you will be synthesizing SIT. So you know phi 1t, phi 2t, phi nt, and you have a multiplier circuit. Let us say you have n multipliers. Now, this multiplication maybe you will be doing it through some op-amp circuit or through other circuits, whatever the way you implement multiplication in hardware. Ultimately, things have to be done in hardware. So you just take the coefficients, that is, you take this Sij's with j lie from 1 to n, and you simply multiply each Si, let us say Si1 with phi 1t, then Si2 with phi 2t, and then finally you have an adder circuit to add all of them. So you get Si. This is a synthesizer for generating the signal Si2. Then you have this analyzer. Now, analyzer, what will it do is that it will try to find out these coefficients. So the purpose, I think the equation which you would use for it is, I think they already written it out, this. So you have to first multiply and then you need to have an integrated circuit. Okay, this you may do through some capacitor, or I think op-amp also does it. So this will be having a finite circuitry for doing it. So first you take SIT, you create its n copies. SIT, you have to create n copies. In each copy you multiply individually with phi 1t, phi 2t, and phi nt. After multiplying this, apply it to n different integrating circuits, which integrate the product from 0 to t. So they will give you the coefficients, or they can give you the projections. Okay. So this is the analyzer for generating the set of signal vectors. So this is pretty much what we need to understand. So let me write it down. So C, for the purpose of completion, let me write it down. Let's see figure 5.3 from Aiken's textbook. So we are covering this thing from Aiken's textbook because he has given it in a, you can say, restricted and useful manner. That would be a better thing to say, restricted and useful. Why? Because whatever we need is being given there and it has been given properly. So you can see figure 5.3 from Aiken's textbook. So let me write it down. Synthesizer is nothing but you can say multiplier and then summer. Multiplier and then summer. You have to just multiply and then sum. And the analyzer is product integrators. Okay, let's say product integrators. You just take the product and then integrate, or correlators. Basically, we will be doing this correlating signals or correlators when you will do the reception of digital communication signals. Then this correlators will come. Okay, correlator simply means that you have to take product of two things, integrate it. That is correlated functions. Okay? And this is a bank of n correlators, or you can say bank of n product integrators. Okay. Now let us go towards the study. So Si bar, now this we have the vector. Now instead of SIT, we would be now preferably working with Si bar, because this gives us a finite, you can say, representation of infinite values, SIT, which it takes from 0 to t, capital T. So SI is called signal vector. This is our signal vector. SIT is called signal vector. So if we extend, this is important to realize that if we extend our conventional notion, our conventional notion, if we conceptually establish, so if we conceptually extend our conventional notion of 2D and 3D, of 2D and 3D Euclidean space, okay, so this is the most fundamental space which we study. Basically from our school days we study this space to an n-dimensional Euclidean space. Basically in our school days we generally study 2D or 3D Euclidean space. जो हम लोग basically we draw two axes, x axis, y axis, or we draw three axes, x, y, z. So what are these two spaces? One is a two-dimensional Euclidean space, and the three-axis one is a three-dimensional Euclidean space. Now, if you assume three-dimensional Euclidean space, we can basically observe, realize, or we can say we can see around us. We are all in a three-dimensional space. But if at all you presume that there can be more dimensions to it, then we come with the concept of n-dimensional Euclidean space. Now, Euclidean space means this Euclid was a scientist who basically I think must have done some work in this. The Euclidean distance, you can say, came up that how do you find distance between two vectors in this space. I think the formula was x1 comma y1 is the representation of one point, x2 comma y2 is the representation of another point. Then the Euclidean distance was under root of x1 minus x2 square plus y1 minus y2 square. So this is what we know. Now we try to extend it to an n-dimensional Euclidean space. We assume that such a space at least is theoretically possible. Okay. Space SIT, you can say, comma SI bar, where I is equal to 1, 2, 3. The number of signals we have taken is m. Is a set of m points. Is a set of, you can say, m points in an n-dimensional Euclidean space. Okay, I think this is simply saying that you have m vectors in n-dimensional Euclidean space. It is quite obvious because each of them is an n-dimensional vector. n dimensions की, और you can say n इसके elements हैं SI बार के, और ये total कितने m हैं, तो हम ये मान सकते हैं कि these are m points in an n-dimensional Euclidean space. With, let me write it down, with, this is important to realize, with n mutually perpendicular or orthogonal, you can say, orthogonal axis labeled phi 1, phi 2 and phi 1. It means जो हमने स्टडी किया था उसमें हम we say this like this. This was my x-axis, this was my y-axis, and this was my z-axis. Okay. And any point I say, let us say if I write this was some x1, y1, z. So this was the standard three-dimensional Euclidean space which we have studied. But in order to have, you can say, a straightforward analogy with n-dimensional signal space, we say that let these axes be signals. Okay. Now these axes are signals, which is phi 1. Let us say this is phi 2, this is phi 3. I am not writing t because t then doesn't hold any significance here, because this is just to have a sort of an analogy to make us understand things. Okay? So आप मान लीजिए कि जो तीन एक्सिस हैं वो आपके तीन बेसिस फंक्शंस हैं, and now any signal which can be generated with the linear combination of these three, I represent it through the signal vector. Okay, now this is a signal vector. Signal vector which we have already defined. This is my SI bar. for the 3 case, for 3 dimension, or you can say for n equal to 3. So this is for n. For more than 3, you can just visualize it, or you can, yeah, visualization simply means that seeing things in your brain. So you can see that you have n axis, and each of these n axis is the basis function, and any vector lies in the space generated by these n basis functions. Why are we having an analogy with the Euclidean space? Because we will see that whatever we do in this Euclidean space, n-dimensional Euclidean space, exactly follows in the n-dimensional signal space. Okay? The distance concept, the correlation concepts, the orthogonality, everything follows word by word. Okay? So this n-dimensional Euclidean space, where the axes are the basis functions, Euclidean space is called the signal space. So now we have said that this is an n-dimensional Euclidean space. Now you will know that on these vectors Si bar, whatever you do on the standard vectors in the Euclidean space we have studied, they all will apply. अब कुछ नहीं है, अब आपको बस एक n डायमेंशनल वेक्टर से काम करना है, और इस वेक्टर की जो एंट्रीज होंगी वो रियल नंबर्स होंगी. अब ये वेक्टर बन के आ गया n डायमेंशनल. Now you have studied these n-dimensional vectors most probably, I think, in your 12th standard maybe. I don't remember if in 12th standard we study vectors of more than 3 length or more than 3 coordinates. I don't know. But if at all we have done for 3 coordinates, तो उसका study आप relate कर सकते हैं. Okay. So let us now define the things. Squared length of any vector. Squared length of any vector in Euclidean space, denoted as is given by simply under root of SI transpose SI under root. Now this transpose, again I would say that this is, we have assumed SI contains all real numbers. If at all it doesn't contain real numbers, it has complex numbers. Let me write it down. If complex, this is equal to under root of, what do? You use a star operation, or I think the better operator is Hermitian. That means both of these. It is Hermitian, because what I think is that once you will go back and read the notes, it should not lead to any sort of confusion. Then you have to use a Hermitian operator. Remember that. Otherwise, this quantity won't be real. This has to be real because you are finding the squared length, and length cannot be complex. So this is equal to, anyways, let me write it down. This is equal to summation. J is equal to 1 to capital N Sij square. Okay, where I is equal to 1 to now this squared length is nothing but the inner product or dot product, of SI with itself. So again, we have now come up with a new term, that is inner product or dot product. Dot product, I know, we all know, because we have studied vectors from our early days, that is school days. But inner product, I think this you must have gone through in the linear algebra course, and I cannot basically start saying anything about it because this will take a lot of time. This inner product, you can simply say that it is equal to dot product, which is whatever dot product you know. The dot product you know is from the standard 3-dimensional vector space. जो आपने x, y, z पढ़ते हैं, उसमें you can simply say that what is a dot b, where a and b are vectors. That is simply a1 b1 plus a2 b2 plus a3 b3. That is what we have for the 3-dimensional space, or for the vectors which have 3 elements. तो ये हम लोगों को पहले इनिशियल डेज से पता है, तो उसी से आप डायरेक्टली इसको एसोसिएट कर सकते हैं. Whatever we have done here is we have taken the dot product of the vector with itself and then taken a square root. This will give us the basically length. So this square root, you have to remember that you have to take the square root, or this norm square or this length square is the dot. Okay, so I now squared length. I should not write the squared length. Length should not be squared because we have not taken the square. So length. So length of any vector in Euclidean space. And then I should write that the squared length is this. Then nothing is there. So squared length is equal to the inner product or dot product of SI with itself. Squared length, क्योंकि अगर इसका square कर देंगे, that is, let me write it down. This is equal to, or SI, summation SI if it is complex. Okay. So I think with this we have defined the notion of, you can say, the squared length or length of the signal vector in the signal space. Now let us relate it to the energy. This is important because if at all we are developing an analogy between the standard Euclidean space with the Euclidean space of signals, we must have the, you can say, corresponding quantities as well. कि अगर energy एक signal की concept होती है तो वो इस vector space में कैसे differ? तो आप simply देख सकते हैं कि note that energy of a signal SIT of duration t seconds is EI. That is the standard, you can say, we know, SI square dt. Okay. Now let us write SIT as what we know. This is integral 0 to t. Summation j is equal to 1 to capital N Sij phi jt into summation k is equal to 1 to n. So I am not writing why I am using two different indexes. I assume you must be knowing this because we are multiplying, so we have to use different index. Otherwise, you won't be able to capture all the terms, okay, of the output of the multiplication. dt. Now this then comes to summation j is equal to 1 to n, k is equal to 1 to n, Sij, Sik, 0 to t, phi jt, phi kt, okay, and this is equal to summation Sij square j is equal to 1 to n, which is equal to norm of, or you can say, square length by. We know that this will give you answer only if at all. So this is equal to 1 only if j is equal to 1 if j is equal to k, 0 if otherwise, or you can say j not, which is 0, because they are orthogonal as well as they have unit energy. So that's why this is 1 if at all j is equal to k. So you just substitute j as equal to k, so you will get Sij square, and then the summation is nothing but sum over only n terms instead of double n terms. The k index isn't here. So we have a straightforward analogy. So energy of a signal SIT is equal to squared length of the signal vector SI representing it. So you can see that if at all you have the concept of energy for these signals, this has an analogous entity in the signal space. The analogous entity is this length. Okay. So energy of the signal is straightforward equal to the you can say squared length of the vector representing the signal in the signal space. Now another thing is we can show that integral 0 to t SIT into SKT. Let us say we take two different signals is equal to SI transpose S on K. That is, what does it mean is that inner product of signals SIT and SKT over the interval over the interval 0 to t using time domain representation is equal to inner product of respective vector representations. SI bar and SK. Okay, so means ये भी एक एनालॉगस क्वांटिटी आपको मिली कि जो आपका टाइम डोमेन यू कैन से दिस इज अ कोरिलेशन यू आर कोरिलेटिंग SIT with SKT. Up to now we have not yet introduced what is correlating two signals is, but for the time being assume this is some sort of an integration over the domain of interest. So the domain is 0 to t. So over 0 to t you are multiplying and integrating. So this is a product integrator you can say or correlator. So product integrator is nothing but the you can say dot product of the two vector representations. So this is another analogous quantity you have found out that in time domain अगर आप correlation करेंगे तो वैल्यू सेम होगी अगर आप वेक्टर सिग्नल स्पेस में दो वेक्टर्स का correlation करेंगे सॉरी डॉट प्रोडक्ट करेंगे सेम अप्लाइज है कि अगर आप टाइम डोमेन सिग्नल की एनर्जी निकालेंगे वो सेम है अगर सिग्नल स्पेस में आप वेक्टर का लेंथ निकालें उसका स्क्वायर करें रिमेंबर दैट the square of the length is equal to energy, not the length itself is equal to energy. That you should remember, otherwise this is a point of confusion generally. Okay. Now with this, let us move to another concept that is, this is important. So note that inner product of SIT and SQT, SIT and SKT, right? And SKT is invariant in the choice of basis functions. Okay, this is a very important factor. I think this you must have studied earlier, but right now it needs to be mentioned because it is important from the context that we must know this basically for our signal spaces. So note that the product of SIT and SKT is invariant to the choice of basis functions. Okay, this is important. It only depends on the components of the signals projected onto each of the basis functions. Okay, this is important. कि जो एनालॉगस क्वांटिटीज निकाली हमने यहाँ पे देखिए if at all we were finding the energy we said that it is equal to simply the squared length of the vector representing signal in the signal space, but there is no mention of the basis functions. We use only two properties of the basis functions. One is that it needs to have a unit energy, each of the basis function, and it must be orthogonal. It means it should be an orthogonal set in which every vector is orthogonal to the other. So we are not at all dealing with the identity of this. मतलब ये कौन से functions हैं इनसे हमें मतलब नहीं है. अगर ये दो property satisfy करते हैं, capital N इनका number है, it suffices for us. Okay, and we can say that for any such choice which satisfies these things, the length is same. So energy is equal to the squared length of the vector. The same applies for this product integrator as well, or the same applies for this correlator as well. That this inner product is not dependent on the choice of the basis functions. Now, when I say basis functions, it implies that is 1 and 0 volts. Or right now, if you have not yet said about the energy, but that is also a prime requirement. Otherwise, that will lead to a scaling factor only, nothing else. एक scaling factor आ जाएगा सब terms में. जो कि वैसे it can lead to some issues, but better is to have them to be orthonormal. That will lead the derivation to be very you can say easy and straightforward. So let us move to the concept of Euclidean distance. So Euclidean distance between points represented by the signal vectors SI और SK bar is so DIK is equal to norm of square, which is equal to N So this is simply the Euclidean distance between point. I think this is straightforward. Nothing to deal with it because this we have just taken up directly from the Euclidean geometry or Euclidean space. One thing to note that it is scalar. Okay, this you should know. Scalar, not a vector quantity. This is just for those who may just skip this important also. Now another important thing to define is the cosine of angle between the vectors. Okay. So cosine of angle between vectors. I think we have already gone through it. Theta ik, which is equal to inner product of two vectors. Inner product of two vectors divided by product of their individual norms. Product of their individual norms. So I have not yet introduced norms. Norms is basically, you can say the two norm. This whatever we are writing, this is of two norm. Two norm is nothing but the length of the vector. Okay. So cos of Yeah. So cos of theta I k is equal to S I bar transpose S k bar divided by the individual nodes multiplication. Okay. I think this is what we have already seen in our earlier days. So the two vectors, Si bar and Sk bar are thus orthogonal, or you can say perpendicular to each other if the inner product, Si transpose Sk is equal to 0. In which case, theta ik is equal to. Okay. There is one point to understand that up to now we know that, let us say, we say that this angle is 90 degree, and it's easy to realize this in a two-dimensional space. Even in the three-dimensional space, let us try realizing it. Now suppose you can say that there is a rectangle which, so I don't know how to draw it more perfectly, but you can see that this is a type of a triangle which is there. Let me write it down: x, y, and z. So in the xz plane, this line is in the xz plane. You can say line in xz. Okay. And this lies in all the xyz, and this is parallel along the y-axis. Parallel along, you can say parallel to the y-axis. That would be a better term. So this will basically make it an easier task to visualize and read it. Maybe after a few days, once you go back and read the notes, this is parallel to y-axis. So then you can visualize that this is the way a 90 degree angle still holds in the three-dimensional space. Now similarly, you can extend it to n dimensions. So that is what is here. You assume that there is a line in n dimensional plane में एक लाइन है और उसको एक लाइन इंटरसेक्ट कर रही है, और दोनों का अगर एंगल हम देखें बीच का तो वो 90 डिग्री होगा. That is what is the concept of orthogonality. And in the case of n-dimensional Euclidean space, the straightforward formula to check it or to show it is that you just take the inner product, that has to be 0. That is 0, it means that they are orthogonal or perpendicular. Better term is orthogonal because this is the more you can take term suited to n-dimensional spaces. Perpendicular is more or less to a two-dimensional space. That's why you will find less usage of perpendicular. Mostly find the usage of orthogonal. Now, another important concept is the Schwarz inequality. So we are doing a few things in vector spaces which are useful for us, okay, means for our course. We are not at all saying that we are studying vector spaces. Otherwise, this itself is a full course. So Schwarz inequality, very important inequality for us because it will help us at least find bounds on functions, because we are anyways studying pulses for communication. Pulses are nothing but functions which are point of interest in 0 to t. जो bit interval है या bit time है, उसके रेस्पेक्ट में हमारा पल्स जो है वो हमारा पॉइंट ऑफ स्टडी रहता है p of t. तो ये जो फंक्शन है in 0 to t, although this p of t is point of interest for the whole domain, क्योंकि आगे तक वो क्या बिहेव कर रहा है वो भी इंपॉर्टेंट है, एज वी स्टडीड इन आवर नाइट क्विज ऐसा ही क्राइटेरिया. बट स्टिल फॉर 0 to t राइट नाउ टू डेवलप थ्योरी 0 to t वर्क्स फाइन फॉर अस. सो लेटर ऑन वी विल सी दैट व्हाट हैपेंस इफ एट ऑल दिस pt एक्सटेंड्स आउटसाइड t एंड हाउ डू यू शो. बट बेसिकली जो 0 to t है ये हमारा सैम्पलिंग इंटरवल भी है. आप जब रिसीवर पे सैंपल करेंगे सो यू विल बी सैम्पलिंग इन 0 to t एक पॉइंट पे सैंपल करेंगे, तो मिड पॉइंट पे सैंपल करेंगे या t पे सैंपल. So what is the Schwarz inequality? So consider any pair of energy signals S1t and S2t. The Schwarz inequality states that this gave us a very, you can say, good inequality which allowed us to bounce on. Let's see. Integration. So right now this Schwarz inequality is for minus infinity to infinity. Okay? We are studying for this. This states that from minus infinity to infinity, S1t into S2t dt. Okay, and we take the square. This is less than equal to integration from minus infinity to infinity S1 square t dt into integration minus infinity to infinity S2 square but this is the Schwarz inequality. Equality holds if and only if S2t is equal to C times S1, okay, where C is any constant. So first of all, the question is that why are we studying it here? Because the proof of this we will give by projecting S1t and S2t. You can projecting it by drawing an analogy between S1t, S2t and their vector representations in the signal space. मीन्स अगर हम S1t, S2t को अपने वेक्टर रिप्रेजेंटेशन से रिप्लेस करेंगे या वो चीज यूज करेंगे तो आप इस इनइक्वालिटी को प्रूव कर सकते हैं. So that's why we are studying this. It simply says that if you are correlating S1t and S2t and taking a square of the correlation, it will be always the upper bounded by. Means इस वैल्यू से छोटा होगा हमेशा. लेफ्ट हैंड साइड विल बी स्मॉलर देन द वैल्यू टुवर्ड्स द राइट. तो अपर बाउंड इस वैल्यू के ऊपर ये एक अपर बाउंड है. अगर ये ग्रेटर देन इक्वल टू होता तो लेफ्ट हैंड साइड वैल्यू पे ये एक लोअर बाउंड होता. लोअर बाउंड मींस इससे बड़ा है. सिंपल हिंदी में कन्वर्ट करेंगे या व्हाटएवर लैंग्वेज यू स्पीक यू कैन इजीली अंडरस्टैंड दिस. So this is less than equal to the product of the, you can say, energies of the signals. This is what energy of S1t, this is what energy of S2t. And so correlation is always less than this, the square of it. So we will study the proof. What is the proof of it? The proof is simple. Let S1t and S2t be expressed in terms of the pair of orthonormal basis functions phi1t and phi2t. Okay, so we are basically studying this proof in a, you can say, I would say, some sort of a looser sense. Why being that it can be easily extended to n basis set. Means phi1, phi2, phi3, phi4, phi8. तो अभी हम दो बेसिस फंक्शंस के टर्म्स में प्रूफ को स्टडी करेंगे, बट इट कैन बी इजीली एक्सटेंडेड टू मल्टीपल बेसिस फंक्शंस. ओके, so S1t, suppose we write it like this: S11 phi1t plus S12 phi2t. Okay, similarly we write S2t as, obviously this Schwarz inequality is for those signals which have finite energies. नहीं तो राइट हैंड साइड पे जो है ये एनर्जीज ही हैं, इसीलिए आई हैव रिटन कंसीडर एनी पेयर ऑफ एनर्जी सिग्नल्स दिस आई थिंक शुड बी प्लेस्ड इन for those signals in which for which energy doesn't have a finite value, this inequality cannot be used. So this is S21 phi 1t plus S22 phi 2. Where phi 1t and phi 2t satisfy the orthonormality condition over the entire time. Minus infinity to now what is S1 bar? That is equal to. Now there is one important thing to realize at this point that can we have examples for it? Yes, you can realize the Fourier series. If you at all you remember Fourier series, the complex exponentials they were of this kind. Okay? They were orthonormal over the entire domain. So you can see that in reality such functions exist. Okay? At least in theory it exists. So reality means theory. So 1, 2, and S2 bar is nothing but. So this is the corresponding vector representation. I think this we know because we have studied vector representation above. Okay. So cos of theta between them, let us write the angle, the cosine of angle between them is nothing but S1 bar transpose S2 bar divided by norm of S1 bar into norm of S2 bar, which is equal to. Now let us use the corresponding time domain representations. Infinity S1t into S2t dt divided by under root integral minus infinity to infinity S1 square t dt under root. I think this you can directly relate to what we have done. I think here we showed it. The two things we studied. Yeah. So this was the energy. So energy is nothing but this. So the square of this is integration over the domain of interest. So the domain of interest of the Cauchy-Schwarz inequality is minus infinity to infinity. And there we have exclusively written that phi 1t and phi 2t satisfy the orthonormality condition over this domain of interest. Okay. So this is this. And secondly, I think we studied this correlations. We just replace this with the time domain representation. That is what we are doing. Minus infinity to infinity S2 square t dt. Now recognize or realize, realizing that cos theta always lies between minus 1 and this we know. So what does this imply? Or you can say the better way to write this is that the absolute value of cos theta is less than 1. This is also another way of using the absolute value operator to write the same thing. Now this implies, what does this imply? This implies, or this has a straightforward implication that cos square theta will be less than equal to 1. There is another way to write the same thing. Now with this as the case, use it in one, use this in one, this in one, and it directly leads to so I think S short inequality, S of I is the short abbreviation for it, or as abbreviation for it. Short. कैसे? अब आप इसको cos स्क्वायर कीजिए तो लेफ्ट हैंड और न्यूमरेटर स्क्वायर अपॉन डिनोमिनेटर स्क्वायर, दैट इज लेस देन इक्वल टू 1, दिस will directly lead to this. Okay, so we have proven one aspect, that this is less than equal to this, but we have not yet proved that in what conditions the equality holds. If at all the equality holds, then this should be the case. Let us see how do you show that. Okay, this is I think straight easy to show. So we know that cos theta is equal to 1 when theta is equal to n pi. Okay, अब ये आपको अगर याद नहीं है, you do not remember it, let me draw the curve for you. So this is the curve, this is 0, this is your pi by 2, this is your pi, this is your 3 pi by 2, and this is your 2 pi. Okay, so you will realize that for pi and for 2 pi plus minus 1, I should write that this should be for theta is equal to n pi. Okay, and I think n should be, I should write positive, negative, integer. This should be like this: -3, -2, -1, and 0 also is an element of this. So absolute value of cos theta is 1. Now, if at all this is equal to +1 or this is equal to -1, whatever it means, if cos theta takes a value +1 or cos theta takes a value -1, you can say that this equality will hold. This inequality will hold with equality. Let me write it down. So when cos theta absolute value is 1, Schwarz inequality holds with equality. So this should be, I think, clear to you कि जो inequality means जो छोटा बड़ा, मतलब छोटा जो है ये लेस देन इक्वल टू की बात है, तो अब ये लेस देन नहीं रहेगा, इक्वलिटी हो जाएगी. तो जब cos theta absolute value 1 होगा, अब इसका मीनिंग क्या है? When theta is equal to pi, n pi, 2 pi, 3 pi, what do you mean? It means that both the vectors lie on the same line. So for theta is equal to n pi, so you may realize this. Suppose if this is 1. If there is another vector and the angle between both of them is 0, so it will be like this. It will be along this line. If the angle between the two is pi, so it will be opposite in direction. But along the same line. If the angle is 2 pi, then again it will flip back and come to this same. Like this continues. So दो ही possibility है, या तो मतलब line में तो होंगे, but they may be in opposite directions. Okay. That is the only possibility. It means they have to be along the same line, but they may have different orientation. Okay. So for theta is equal to n pi, both vectors must lie on a line. Must lie on a. That is, we may express, since they are on the same line, so we may express them as S2 bar is equal to C times S1 bar, where C is a scalar. That is, S2t is equal to C times S1. If where C is a constant. Now, one important thing to say here is that we said in the statement that it is an if and only if condition. So we have not proved this by the standard strategy of proving if and only if statement. That is, if first of all we take that if this is the case, then this holds, and if this holds, then this should be the case. We have just used a very simple way, that is whatever we have learned for the signal space. And I basically at the start of the proof I said that it may seem to be a loose proof, But our purpose in this course is not to prove this, it's just to understand that how our vectors concept of signal space helps us showing that this works. So it must be there that if at all we have not done it that way, so that was not required at the moment. So with this as the base, we need to move to the main procedure which we want to study. That is the Gram-Schmidt orthonormalization, orthogonalization process. Schmidt orthogonalization procedure. I think we have already gone through this, maybe in the ICT course, Introduction to Communication, ICS course, Communication Systems. But we will do it for the sake of completion because this course needs. So for this, we will study a small, you can say, concept again from vector space. That is the concept of component of a vector along another. Okay, this is an important concept which we need to study. So we first study component of a vector along another vector. So let us consider two vectors. G bar and X bar, suppose. Okay. And let us assume that this is your X bar and suppose this is your G bar. And suppose this is another vector which is like this. And this is your some vector. And suppose this is your C X bar. C is a scalar. This is some sort of an origin. Now, if at all we have studied projections in some other course, so we know that component of G along X. Component of G along X is, let it be, I think it should not be, is C of X bar. Okay. Geometrically, let me write it down, then I will try to explain it. Geometrically, the component of G along X bar is the projection of G on X bar and is obtained by drawing a perpendicular from the tip of G on the vector X. Basically, we started from this point. I think this you must have gone through in the course in algebra where projections are taught. So this projection simply means ये orthogonal projection होती है. Orthogonal projection means कि जो आपने ये draw की है line, this at the point wherever this intersects this vector X, that becomes the projection of G onto this, and this line has to be a perpendicular. Means आपने इसके tip से एक perpendicular line start करी draw, and while drawing at whatever point you intersect this X, so from origin to that point becomes your projection of G on X. Or what we can say is that G can be written as, if at all this is your vector E, so you can write that G bar is nothing but Cx bar plus E. So Cx bar is what? It is, or this point is the point which is nearest to G on X. Another interpretation. अब ये देखेंगे हम लोग कैसे. Okay. So the question is, we would write the question. What is the mathematical significance? What is the mathematical significance of a component of a vector along another vector? Okay. So this is what is the question is. Now we will see, let us see the different possibilities. So this is, I am taking it from Latti's book, but I think by somehow the figures are missing from that book. So one figure I have drawn, let me draw two more figures. Now suppose this is your X, okay, and this is your G. So one possibility is this. Okay, so this is your E1 vector. This is your G vector. Okay. And this is, suppose, your C1 X vector, and this is your X. And another possibility is this. E2 vector. Okay. This is G vector. This is C2X X vector. So this is, let us say, possibility 2, this is possibility 3, and this is what is possibility 1. So from the perspective of these three possibilities, we need to basically study that what projection is, what do you know, okay? So these two show two of the infinite possibilities. Obviously you will have infinite possibilities. मीन्स आपको G और X गिवन है, अब आप ये अलग अलग कितनी सारी लाइंस ड्रॉ कर सकते हैं ऐसे आप मतलब ऑब्ट्यूस एंगल की, एक्यूट एंगल की, आप कितनी सारी, एक्यूट इन द सेंस फ्रॉम X you can draw several lines. Okay. So the unique representation in the question of here, there is no unique representation. So it's true of the infinite other possibilities. So from the perspective of vector addition, to get another vector which is the best decomposition. Okay. So this is the question which we would start with in our next class. Okay, so we stop basically at this point where we have raised a question. Okay, and from next class onwards, we will first answer this, we will complete gram split, and immediately we will start with the random process. In the next lecture, we would definitely start with it. Okay, so I think we are done for today. If at all you need to talk to me, you can stay back. I am there.